So, welcome back. In the last part of the lesson, we talked about the first principles definition of the derivative, essentially how to find the equation to tell us the slope of the tangent at a point. So it's going to give us a lot of information about the rate of change of a function, which can be quite useful. And we're going to see that in this part of the lesson. We'll deal with some real-life problems. And we're also going to talk about a bit more about notation and the different ways that we represent things in calculus. Before we do that, though, we are going to start off with a little story. Anyways, here goes. Once upon a time, back in the days of the age of scientific advancements, back in the 1600s, there was one mathematician named Sir Isaac Newton, who we've talked about before. In fact, we talked about how he was actually sent home as a student at Cambridge because they were battling the bubonic plague, much like we are fighting COVID-19 currently. And during that time, he founded a whole branch of mathematics because he was discovering all sorts of problems that he couldn't resolve through the mathematics that existed in the day. Things like when you drop an apple, why does it continually speed up as it approaches the ground? Or how can I chart the path of planets as they orbit around the sun, and things like that. In order to do that, he developed this whole new branch of mathematics called calculus. There's differential calculus and integral calculus. Differential we deal with in this course, and integral you'll see a little bit later. But the part of the story that you probably didn't know is that at that time, in fact, in the same year, he was not the only one that was starting to discover calculus. In fact, there was another mathematician over in Germany. Sir Isaac Newton was British, and another mathematician over in Germany was starting to work on this at the exact same time, and his name was Gottfried Leibniz. Now, Gottfried Leibniz, he actually did not work with Newton at all. The fact that they were creating this branch of mathematics exactly at the same time is a complete coincidence. We're not quite sure how that all happened, but essentially, Newton is credited with being the first one to have discovered it, but Leibniz was credited with being the first one to publish it. But even though they hadn't communicated on this, they had discovered it independently of each other in pretty much a very short amount of time. So what happened was we started to develop different forms of notation because people tended to credit one versus the other, and people use different notation. And in fact, as of today, Newton's notation isn't really used very much, but we use function notation for when we talk about Newtonian calculus, and we tend to use a totally different notation when we talk about Leibniz. So in his, he used this instead. He used that in place of f prime of x, essentially mean the same thing. Sometimes in his original notes, it looked more like dy by dx. So in fact, it's all it means is it comes from the Latin word for difference. I believe differentia. The other way that the other thing that comes out of it is delta. It means the same thing, delta y over delta x. So all of them essentially mean the same thing. When we talk about Leibniz notation, we're talking about representing things with dy by dx, or whatever variables we happen to be using. The y is going to be exchanged for whatever dependent variable we have, and x is going to be exchanged for whatever independent variable we have. Sometimes we represent it with d by dx of fx, means the same thing. Or our last option, if we're looking at a specific point, we could represent it the value of the derivative when x equals a, or dy by dx at x equals a. All three of them work the exact same way, and they represent the exact same thing. But essentially, this was the notation that was being used by Leibniz when he created this. And because it took a very long time for historians to credit both of them equally with the discovery, people tended to favor different forms of notation, and as a result, our notation became a little bit jumbled. So through the rest of this lesson, we're going to get some more practice using Leibniz notation, just so we have a bit more practice with it and you know how to use it. At the same time, we're going to deal with some word problems that where we can take this knowledge of calculus and apply it to some real life problems. So, the first example, the path of a golf ball in the air is modeled by the function h of t is equal to negative 5.6t squared plus 4.6t minus 2, where h is the height in meters and t is the time in seconds. The first thing it asks is to determine the rate of change of the height of the ball at time t. Express the derivative using Leibniz notation. So first thing I want to point out is when we see rate of change, we were talking about the slope of the tangent, or in this case, from now on, when you hear rate of change, think derivative. So from here, let's use that first principles definition. So luckily, outside of the first part of this, it's exactly the same notation. So we said dy by dx. In this case, we're not dealing with x's, we're dealing with t's. So, and we don't really have our dependent variable here, so we can call it y. We wouldn't do dh of t. We don't really worry about that. So this is going to be dy by dt, and it's going to be the limit as h approaches 0. And then we're going to do h of t plus h minus h of t over h. Don't get thrown by the fact that there's a lot of h's here. Just keep track of which ones are capital, which ones are lowercase. That's going to be negative 5.6 t plus h squared plus 4.6 t plus h minus 2. So let's write that into the definition. So we said usually it's f of x plus h, or in this case, h of t plus h. So negative 5.6 t plus h squared plus 4.6 t plus h minus 2 minus h of t. So that's going to be minus negative 5.6 t squared plus 4.6 t minus 2 all over h. So now, we said in the last lesson that our big goal is always to try and get rid of that h in the bottom, because until we do that, we can't simplify this limit. It's impossible. So let's simplify the top, and maybe that will help us a bit. So let's go left to right. Let's see what we can do with this. So we can start by expanding out that t plus h squared. That's going to be t squared plus 2ht plus h squared. We could expand out the next term. So it's going to be 4 plus 6t plus 4.6h minus 2. And then we can flip all the signs in the next set of brackets. So it's going to be plus 5.6t squared minus 4.6t plus 2 all over h. Let's do a bit more with this. Let's expand out that first bracket. So that's going to be minus 5.6t squared. Then we're going to do negative 5.6 times 2, which is negative 11.2 ht plus h squared. And then the rest, we can't do too much with it right now. You could try collecting like terms, but let's just do it all in one step next. 2 plus 5.6t squared. Just keep writing out all the rest of this line all over h. Okay, this is starting to get a little messy. Let's see what we can do here. So let's see. Right now we can get rid of, we have a positive and negative 5.6t squared, so those can go away. We have a positive and negative 4.6t, and we have a positive and negative 2. So all those can go away. Let's see what we have left. Now we have, if we combine all this, we get as only one ht, which is negative 11.2 ht. And let's see, we're going to have a minus 5.6 h squared. Whoops, that's a problem. I forgot to multiply this by minus 5.6 h squared. So that's going to be minus 5.6 h squared. And then we have just the 4.6 h all over h. And don't forget your limit definition at the very beginning. And now you'll notice everything here divides by h. So now we get the limit as h approaches 0. And that's going to be negative 11.2 times t minus 5.6 times h plus 4.6. And lastly, plug in that h equals 0. The middle term disappears, and we're left with negative 11.2t plus 4.6. That's equal to dy by dt. So now we have found a formula that's going to tell us the rate of change of this golf ball. In fact, we know that rate of change also means speed. So essentially, this formula is the speed of the golf ball at any given point in time. So the next part is asking us to determine the rate of change, or the speed, at 0.6 seconds. So we're going to say that is dy by dt at t equals 0.6. That's going to be negative 11.2 times 0.6 plus 4.6. So we multiply that out, and that's going to be negative 2.12 meters per second. So therefore, the speed of the golf ball at 0.6 seconds is negative 2.12 meters per second. So what that means is that the ball is traveling downwards at a rate of 2.12 meters per second at that point. And lastly, if we want to discover the equation for the tangent line in 0.6 seconds, we could do that too. So the way we do that is we know that our tangent line is to be represented with y equals mx plus b. So let's gather up what information we do have here. We know that x and y, actually we're going to use t instead of b, since t instead of x, because we're using t's in this one. So we know that t is going to be 0.6. And we said to find the slope of the tangent, we're just going to use the derivative. And we did that in the last part, so that's going to be negative 2.12 meters per second. So now we need to find our b value, but there's no easy way to do that. So let's see if we can figure out the y value. As it turns out, the y value is just the height at that point. So it's going to be the same as h of 0.6, the original function, not the derivative. So the height is going to be determined by the original function, which is going to be negative 5.6 times 0.6 squared plus 4.6 times 0.6. And then minus 2. And when you punch all that in, you should get negative 1.256 meters. So now we have an x, a t, and a y, a t, and an m. Now we can just solve for b. So let's see, if we're going to plug all that in, it becomes negative 1.256 equals negative 2.12, and t is 0.6 plus b. You rearrange all that, and you should get negative 1.328 as your y-intercept. So now we have the slope, we have the y-intercept, we have enough to make the equation of a line. So therefore, equation of the tangent at t equals 0.6 seconds is y equals mx plus b, so negative 2.12 times t minus 1.328. Next question asks us, when does the ball momentarily stop? What is the height of the ball at this time? So essentially, when is the rate of change or the speed of our ball 0? And it's a little, this probably doesn't feel like it makes a lot of sense because we know that the ball is constantly moving, but we know that there's a point right in the middle where it reaches its maximum height. It's not going up or down. It's just kind of stuck in midair. Not really, but just for an instant in time, the speed is 0. It's not going up, it's not going down. So we're looking for that point. So the way we're going to do that, we're going to say that at that point, our derivative is going to be equal to 0. So to do that, let's take our derivative function that we found in part A, and that's going to be negative 11.2t plus 4.6. But we're going to take that dy by dt and we're going to replace it with 0. So rearrange this, move the 4.6 over, and we get negative 4.6 equals 11.2t, or t equals 0.41 seconds. Let's try one more thing here, one more important piece of information that's good to know. So we can also have points that are not differentiable. Not differentiable means that we cannot calculate the slope for a tangent at that point. So to do that, let's look at the function y equals x plus 5 for x is less than or equal to 2, and y equals 0.5x plus 2 for x is greater than 2. Another one of those piecewise functions that we saw in a couple of the lessons. Let's use that to help us. So question A asks, from the graph of this function, what is the slope as x approaches 2 from the left and from the right? So that's not difficult to find out. They're both linear functions. So on the left, we're going to look at, let's see, the function on the left is y equals x plus 5. So m is going to be equal to 1. Looking on the right, the function is y equals 0.5x plus 2. So the slope for this one is 0.5. So question B asks, what does this tell you about the derivative at x equals 2? And the real big question we have is here, even if they do line up, they may be two lines that actually intersect at this x equals 2, but it looks like the slopes are totally different. So if we were to try and draw a tangent to this, which slope would we use? So it doesn't really make sense. So because we have different slopes, we cannot find the derivative for this. So we say that this one is not differentiable, at least at this point. And the last part of this, now we just explain this using just kind of common sense, but we like to be a bit more mathematical about it. So we're going to take that and we're going to prove it using first principles. So what we're going to do is we're going to take this and we said the limit for this function is going to be dy by dx is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. But to do that, we don't have one single function here, we have two, and they're different on either side. So what we're going to do is we're going to look at the left hand and right hand limits and see what happens. So the limit as h approaches 0 from the left is going to be, let's clean it up a bit. Dy by dx is equal to limit h approaches 0 from the left, which is x plus h plus 5 minus x plus 5 over h. And we'll do the same thing from the right. So we'll save the other one for just a moment. Let's deal with the first one. So let's look at this. We have an x and a negative x, so they cancel. We have a 5 and a negative 5, so they cancel. So we're just left with h over h, which is the same as saying the limit as h approaches 0 of 1, or just 1. So on the right side, we have 0.5 x plus h plus 2 minus 0.5 x plus 2, all in brackets, over h. So for this one, we have 0.5 x plus 0.5 h plus 2 minus 0.5 x minus 2, all over h, which is the same as saying we're going to cancel x, the x's are going to cancel, the 2's are going to cancel, and we're left with 0.5 h over h, or just 0.5. So in this case, the limits from the left and the right are two totally different values, and we said that if the left hand and right hand values are not equal, the limit does not exist. So the limit as h approaches 0 from the left and from the right is totally different. X is not equal to the limit as h approaches 0 from the right of f of x So I'm actually going to write that a little bit better. We can use better notation here. So I'm going to rewrite that as the limit as h approaches 0 from the left of f of x plus h minus f of x over h is not equal to the limit as h approaches 0 from the right of x f of x plus h minus f of x over h. The left-hand limit is not equal to the right-hand limit. Therefore, the limit does not exist. So if we can't find a limit using our first principles definition, it means that we cannot find derivative for this point. So, not differentiable at x equals 2. So, long lesson. Hopefully it all made sense. If you're not sure, shoot me an email, ask me some questions, or visit me on the video chat and we'll get it all sorted out. And please make sure you spend some time and practice these, especially the first principles definition. That's all for today. Thank you so much. Take care.